Hello friends, let us start remaining part of chemical equilibrium. Now we are going to start important point, equilibrium constant. And for that consider a general reversible reaction A plus B, reversible arrow gives us C plus D. In forward reaction, A and B are the reactants. In backward reaction, C and D are the reactants. And while in forward reaction, C and D are the product and A and B are the reactant. Let active mass of A, active mass of B, active mass of C and active mass of D. Active mass, already we discussed, active mass is nothing but molar concentrations and it is indicated by enclosing the symbol of solute in square bracket. This square bracket is nothing but molar concentrations. Now apply the law of mass action first of all to forward reaction and we get RF. Rate of forward reaction is directly proportional to the product of active mass of A into active mass of B. As you know, law of mass action states that a rate is directly proportional to the product of active masses of reactants. We can write this equation in another way also. RF equal to K1 into active mass of A into active mass of B, where K1 is a rate constant of forward reaction. K1 is a rate constant of forward reaction. Similarly, apply the law of mass action to backward reaction. As well, in backward reaction, C and D are the reactant, and therefore we get RB equal to, RB, first of all, RB is directly proportional to the active mass of C into active mass of D, where RB is nothing but rate of backward reaction. We can write this equation in another way also. RB equal to K2 into active mass of C into active mass of D, where K2 is a rate constant of backward reaction. K2 is a rate constant of backward reaction. Now, then we know at equilibrium, rate of forward reaction and rate of backward reaction are exactly same. Therefore, we can write at equilibrium RF equal to RB. Rate of forward reaction are exactly equal to rate of backward reaction. Then we have the value of RF, RB. RF equal to K1 into product of active masses of A and B. Substitute the value of RF here. K1 into active mass of A into active mass of B equal to, again we have the value of RB. RB equal to K2 into active mass of C and active mass of D. K2 into active mass of C into active mass of D. we substitute the values of Rf and Rb. Then rearrange this equation, we can write K1 upon K2. Transfer that K2 towards left hand side, it becomes in denominator. Then K1 by K2 equal to active mass of C, active mass of D upon this product transfer to right hand side, and it becomes in denominator active mass of A into active mass of B. Just we mention K1 and K2 are the constants, and therefore a ratio of two rate constant is again constant. A ratio of two constant is again constant, and that constant is denoted by Kc, and therefore Kc equal to, we can write K1 upon K2 equal to active mass of C into active mass of D upon active mass of A into active mass of B. This is our main equation. And this Kc is called equilibrium constant. Equilibrium constant. And thus the equilibrium constant is nothing but, equilibrium constant is defined as, it is the ratio of two rate constant. Ratio of rate constant of forward reaction and rate constant of backward reaction. I will repeat the same. Equilibrium constant is the ratio of two rate constants, that is the ratio of rate constant of forward reaction and rate constant of backward reaction. Or concentrate your on this ratio. Equilibrium constant is also defined as, it is the ratio of product of active masses of product to the product of active masses of reactants. I will repeat the same. Equilibrium constant is also defined as, it is the ratio of product of active masses of product to the product of active masses of reactants. Therefore, we will write in short, equilibrium constant is the ratio of two rate constants, that is a ratio of rate constant of forward reaction to the rate constant of backward reaction. Is it clear? Ratio of two rate constant, that is the ratio of rate constant of forward reaction to the rate constant of backward reaction. This statement we can report in another way also from this ratio. It is the ratio of product of active masses of product of active masses of product to the product of active masses of reactants. reactants. This is the simplification, right? Product ratio of product of active masses of product to the product of active masses of reactants. It is all about equilibrium constant. Now further simplification, if we consider the number of moles of reactants and products, that is number of moles of reactants, that is small a, capital A, small b, capital B, small c, capital C, small d, capital D, where small a, b, c and d are the number of moles of capital A, capital B, capital C and capital D respectively. I will write in short, where small a, b, c and d are number of moles of capital A, capital B, capital C and capital D respectively. Then according to these number of moles, we can write equilibrium constant. We can write equilibrium constant as Kc equal to active mass of C raised to small c, active mass of D raised to small d, active mass of upon active mass of A raised to small a, active mass of B raised to small b. This is the simplified form of equilibrium constant if we consider number of moles. To explain this, if we consider one example, N2 plus thrice H2 gives twice NH3. We consider now number of moles. To explain this formula by using this example, for this reaction we can write its equilibrium constant Kc equal to product of ammonia, right, raised to its moles 2, means number of moles of ammonia is 2, therefore raised to 2, raised to C and D raised to 2 upon concentration of N2, means square bracket active mass, raised to 1. If 1, it is not necessary to write 1, but we written for simplify 1, then into active mass of H2 raised to 3. As you know, number of moles of hydrogens are 3, therefore raised to 3. This is the simplification by using this formula. Now listen carefully one more point. In terms of gaseous reaction, concentration is expressed in terms of atmospheric pressure for gaseous solute. For gaseous solute, concentration is expressed in terms of pressure. Therefore, we can write equilibrium constant for gaseous reaction. Kc equal to, instead of writing this active mass molar concentration, we will write P, because molar concentration is expressed in terms of pressure. Therefore, P C raised to C. Again, similar active mass of D means P D raised to small d upon P A raised to small a P B raised to small b. Why it is so? Because this molar concentration, square bracket, active mass is expressed in pressure, in terms of pressure, in which reaction? Gaseous reaction. I will repeat the same. For gaseous solute, its concentration is expressed in terms of atmospheric pressure. Therefore, we written P instead of square bracket. This is the simplification, right? Any doubt about equilibrium constant, right? P means concentration. Now, then next point is relation between equilibrium constant Kc. This Kc we can report in another way also, Kp. Equilibrium constant in terms of pressure means pressure equal to P C raised to C P D raised to D upon P A raised to A P B raised to B. This Kc we can report in another way also, Kp. Now we'll discuss now relation between Kc and Kp. Relation between Kc and Kp. Relation between Kc and Kp. This Kc belongs to active mass, this Kp belongs to pressure. Now we know that Kc equal to active mass of C raised to C, active mass of D raised to D upon active mass of A raised to A, active mass of B raised to B. We know this equation already we discussed in previous point. Suppose this is the equation number 1. And we know just we discussed Kp equal to P C raised to C P D raised to D upon P A raised to small a P B raised to small b. Equation number 2. Equation number 2. Now we know again one more information for ideal gas equation. Ideal gas equation, PV equal to nRT, where P is a pressure, V is a volume, where N is a number of gaseous moles, R is a universal gas constant, and T is absolute temperature. Then we can write this P equal to N by V RT. Transfer this V towards right hand side, it becomes in denominator. And remember one thing, earlier we discussed meaning of molar concentration. Number of moles per unit volume of solvent is called molar concentration and denoted by C. Therefore, we can write as N by V is nothing but C. As N by V is nothing but C, and therefore we can write P equal to C RT. Again, we know the R gaseous constant and T absolute temperature. Absolute temperature. Now, P equal to CRT. As you know, N by V equal to C. Then substitute this value in this equation. Value of P in this equation. Right? C is nothing but concentration. Yes, sir. Kp by putting the value of P in equation 2, we get Kp equal to, now listen carefully, now concentration is very important here. What is the value of P? CRT, right? CRT. What is the C? Molar concentration. And what is the molar concentration? Active mass. And what is active mass? Means square bracket. And therefore, we can write square bracket. This C is nothing but square bracket. And this C. And we know RT. Whole bracket raised to C. Whole bracket raised to C. Similarly, this P is nothing but C in square bracket. D RT raised to small d upon square bracket A RT raised to small a square bracket B RT raised to small b. Means we substitute the value of P in equation 2, we get this equation. Then simplify it. We can write Kp equal to, split it, active mass of C raised to C RT raised to small c, active mass of D raised to small d RT raised to small d upon active mass of A raised to A, split it, RT active mass of A raised to A, active mass of B raised to small b RT raised to small b. We split that information. Now, again split it. It is equal to active mass of C raised to C into active mass of D raised to D, RT common. We'll write in next common, RT raised to C, RT raised to small d upon active mass of A raised to small a, active mass of B raised to small b into RT raised to A RT raised to B. Right? Now, we can write this in another way also. This another way also. Kp equal to, I will write here, Kp equal to, we know, what is it? Compare this value with equation 1. This is nothing but Kc. Therefore, by using equation 1, we can write Kp equal to Kc into RT common, RT raised to power C plus D upon RT again common, RT raised to small a plus b. Again, this equation we can write according to mathematics. Kp equal to Kc into RT raised to C plus D. RT common. Transfer this a plus b towards numerator. It becomes in minus sign. Therefore, minus in bracket a plus b. Or Kp equal to Kc RT raised to delta n. This delta n is nothing but change in number of gaseous moles. Change in number of gaseous moles means number of gaseous moles of product minus number of gaseous moles of reactants. And this is the relation between Kp and Kc. I will write where delta n is a change in number of gaseous moles, and change in number of gaseous moles can be calculated as number of gaseous moles of product minus number of gaseous moles of reactants. And where R is a universal gas constant, it have three values: 1.98 calories or 8.314 joules. And you know, T is a absolute temperature, and that is nothing but a small T degree Celsius plus 273 Kelvin. These are the absolute values. Right now, I will repeat the same in short. Relation between Kc and Kp. We know that Kc equal to active mass of C raised to C, active mass of D raised to D upon active mass of A raised to A, active mass of B raised to B, equation 1. And Kp equal to P means pressure, that is a concentration in case of gaseous solute. Pc raised to C, Pd raised to D upon Pa raised to A, Pb raised to B, equation 2. For ideal gas equation, we know Pv equal to nRT, where P is a pressure, V is a volume, N is a number of gaseous moles, R is a universal gas constant. We mentioned values 1.98 calories and 8.314 joules. And T absolute temperature, that is small t degree Celsius plus 273, and V is a volume. Then rearrange this equation. P equal to N by V. Transfer this V towards right hand side, it becomes the denominator N by V. And as N by V is nothing but molar concentration, that is active mass. P equal to then CRT. C is the molar concentration or active mass. We know active mass written in square bracket. By putting the value of this P in equation 2, we get this. Kp equal to active mass of C RT whole raised to small c, active mass of D RT whole raised to small d upon active mass of A RT whole raised to small a, active mass of B RT whole raised to small b. Simplified. Kp equal to concentration of C raised to C RT raised to small c, active mass of D raised to small d RT raised to small d upon active mass of A raised to small a RT raised to small a, active mass of B raised to small b RT raised to small b. Then again simplification. We can write this small active mass of D with this C. Active mass of C raised to C, active mass of D raised to D, RT raised to C, RT raised to D upon again this B with A, active mass of A raised to A, active mass of B raised to B, RT raised to A, RT raised to B. Then by using equation 1, we have the value of Kc. And this is the value of Kc. Therefore, we can write Kp equal to Kc. Instead of this ratio, we can write directly Kc. Then RT common raised to C plus D, RT common raised to A plus B. We transfer this A plus B towards numerator, it becomes in minus. Therefore, Kp equal to Kc RT raised to C plus D minus A plus B. And this difference we can write by delta N. And this is our main equation. Kp equal to Kc RT raised to delta N, where delta N is a change in number of gaseous moles. And it can be calculated number of gaseous moles of product minus number of gaseous moles of reactant. It is all about the equilibrium constant. Yes, thank you. Yes, we'll stop here.